So yeah, I'll be talking about reasoning about reversible quantum circuits using our tool QWIRE. And this is joint work with Jennifer Paykin, Lee, and Steve Zdancewic at the University of Pennsylvania. So I'm sort of going to be addressing two questions. The first one is, how do we safely manage ancilli, which are these scratch qubits that tend to be used throughout quantum computation, maybe in a not very safe way? And two, how do we write verified reversible circuits? So let me talk first just a little bit about reversible circuits. So there's a pretty well-known trick. If we want to write a classical program within a quantum circuit, we can we basically do the classical operation and XOR it with an auxiliary qubit. So that, in this case, I'm showing what a reversible AND is. Everyone has seen this probably. It's simply a Toffoli gate, and we have a scratch qubit, which gets the result XORed onto it. So what happens if we want to, say, do an AND of X, Y, and Z? Well, we can't just use a Toffoli, and let's pretend for the moment that we don't have a triply controlled NOT gate. So what we're going to do is we'll introduce a scratch qubit initialized at in the zero state. We will apply a Toffoli to the first two qubits, putting the result on this wire over here. We'll now do another Toffoli. And okay, we've got X, Y, and Z XORed to the auxiliary qubit. So, and now obviously we don't want X and Y hanging around here. We're going to reverse that operation by another Toffoli. So now everything is great, right? No, things aren't great at all. This is garbage, in fact. I mean, it's a garbage qubit, but it's also like, I know how I can say initialize zero. That's a valid, operation. I'm creating a zero qubit and sticking it on my wire. However we do this, given the actual model. But I don't know what it means to say throw away zero. Generally, I can't make my program variables be what I want them to be by fiat. So what is this zero hanging around at the end of my circuit? So sort of the standard answer is that these are assertions. So how does an assertion work? So in a classical programming language, I'll say something like assert x is equal to 0. And I mean by that, fail if x is not equal to 0. In the quantum setting, I could say assert 0q, where q is some qubit, but I'm not sure what that means. That means measure q and then fail if q wasn't 0, because the measurement's going to disturb the state, right? So I can't just fail if it comes up 1. I have to fail if it disturbs the state, and I can't really do that, right? So I find myself in a bit of a situation here. So kind of how have people dealt with these so far? So here's a quote from the famous ReQWIRE paper by Sullinger, Valiron, Ross, Green, and Lonsdale. It is the programmer's responsibility to ensure that only the correct assertions are made. So that's a lot of responsibility. I personally don't want that responsibility. So let's fast forward 5 years to maybe a little bit something even newer and more modern. Oops, something changed there. Okay, I'll use. It's a talk from QPL 2018. The user must ensure that the borrowed qubits are returned to their original state. This is about Q sharp. Okay then. So I'll leave this sort of issue sort of hanging. So we have this language QWIRE, and let me briefly just tell you what you need to know for this talk. So it's a functional quantum circuit language. That means we write it in a functional style. It's embedded inside the Coq proof assistant. It is equipped with the denotational semantics, and more than being equipped with the denotational semantics, it's got a translation function that allows us to actually translate our circuits into that denotational semantics. And, well, now it has ancilli. So let me give you a taste of the semantics of ReQWIRE. So if we apply a gate to a given qubit, I'm going to assume that all the states are of the right size, just because it means I don't have to include identity matrices and Kronecker products everywhere. So if I apply a gate to a density matrix rho, that's equal to applying the corresponding matrix, multiplying it on both sides. If I apply init 0, that's initializing a new qubit, that's expanding the state size by 1, and I'm going to have now a 0 at the beginning of it. If I measure it, that keeps the size, that basically turns a qubit into something that is classical. So basically I project out both the 0 and 1 versions and I combine them in a mixed state. If I discard a qubit, then this is similar to the measurement, except I'm actually shrinking the size of the state. So you see there that we have a 2 by 1, or 1 by 2 matrix at the beginning and 2 by 1 at the end. So we're going to shrink the size. We're going to exclude one's qubit from both sides of what is a mixed state here too. And there's sort of, you can see sort of an implicit measurement because discard looks very much like measure that we're projecting up with the 0 and 1 states. So that's sort of the denotational semantics of ReQWIRE as it was pre-Ancilla. So now we're adding Ancilla to the language, and we have to sort of decide how we're going to do this. So there's two, what I think are reasonable denotational semantics for ReQWIRE with Ancilla. So everything is the same, except now we have this assert 0. And in this semantics, it's a trusting semantics. In other words, what is the semantics if I believe that that is in fact a 0? Well, then I really just have to remove this 0 qubit from the state, and I get a smaller matrix. And this is nice, because as you can see, these init 0 and assert 0 correspond very neatly. They reverse one another's operations. So that's kind of what you would like the semantics to be, assuming that these assertions are all valid. Now, I might also be a little bit suspicious, though. And if I'm not certain that the assertions are all correct, then I would write a somewhat different semantics for assert 0. And that semantics would just be exactly the same as discard. So there would be an implicit measurement, and we're discarding the qubit, and it sort of prevents things from going wrong. You know, there's nothing wrong with discarding qubits, assuming you discard them properly. And as you can see, these are the same operation. So let's get back to this question of how do I ensure that these Ancilla are removed safely? So there's a lot of different approaches we can take, and some of which have been looked at. So one is to use syntactic notions. So for instance, if I initialize a qubit at 0 and then immediately assert that it's 0, then that's fine, because it was just 0. I can maybe extend this a little bit, like if I have an equal number of C-naughts on the left-hand side and an equal number of C-naughts on the right-hand side, or knots on each side, and some controls in the middle. That's also going to return it to its original state. But the problem with this notion of safety or correct assertions is that it's very limited, and we're never going to capture all of the ways that an assertion can actually be correct. Another thing we might try to do is use sort of local semantic notions, which is, so for example, suppose I have some circuit C and it ends with a 0. Well, if the semantics of that circuit is the same as if I had measured that qubit and then discarded it and then started another 0 and then asserted 0, if that didn't change anything, well then I would know that that was actually a 0 qubit to begin with. But that's also sort of hard to work with because, you know, it's hard to reason locally about sections of a circuit, and that's also somewhat an annoying transformation to make. It adds sort of computational overhead. So, but I shouldn't be offering all these notions because I think I've already, maybe some of you caught it, given you a nice notion of Ancilla being correct on the previous slide. We have these two assertions, and one of them is trusting and one of them isn't trusting. So they both go wrong in very different ways. But if the assertion is true, they both have identical meaning, right? Because if this qubit is in the 0 state, that right-hand side of the equation is going to be a 0 matrix. So ergo, what we're saying then is that all of this ancilla are going to make correct assertions at termination if the trusted semantics is identical to the distrustful semantics on the same circuit. An equivalent way of saying this is that if this trusted semantics does not decrease the trace of our density matrix, that is, it doesn't accidentally discard part of the state, well then, that's also a guarantee that all of our ancilla have been used correctly. And in fact, these two notions are identical to one another. And why is that? Because we've shown that our distrustful semantics is a proper superoperator. That is, it is always trace preserving. So if the trusted semantics is equal to the distrusting semantics on the same circuit, well, then the trace is going to be 1. Likewise, the trusting semantics is non-increasing, so it could potentially decrease somewhere, but there's no way to increase the trace of your density matrix. So if that winds up being 1, that's going to mean that it's exactly the same semantics as for your distrusting semantics. So that's great. So once we have that, now we can start talking about syntax, right? So we can prove in terms of our denotational specification for what it means for an assertion to be right, that, say, if I ever initialize an ancilla at 0, apply a unitary, then apply that unitary's adjoint, well then I'm going to get out a 0. And I can maybe do more sophisticated things, like a circuit followed by, you can control some number of targets, and then something called the restricted inverse, which is basically doing the operations in reverse, skipping ones that are just controls on further wires. That's also known to produce an ancilla that's in the 0 state. The restricted inverse is something I took from a paper by Matt Amy and Martin Rothiller.
Are you sure? Because if C is the symmetry map, then this is just going to not return it in state 0, right? But there might be further restrictions on the shape of C.
Oh yes, there are in fact. I momentarily forgot to specify that these are in fact include entirely classical gates. So this is pretty restrictive still. So it would be worthwhile having even further notions, and some of those might call back to the semantics. So like we could say if 2 circuits are equivalent, then we can maybe do one and then the reverse of it, and we'll still have something that's syntactically valid. So there's quite a bit to be done on that. Did somebody else have a question? Yeah. So obviously none of these are going to be necessary for an ancilla to be in the 0 state. I don't think we certainly can't efficiently have a proof procedure that will tell you whenever an ancilla winds up being 0. So these are always going to be sufficient syntactic conditions, but some of them will be very convenient ones. So one example of this being convenient is we might use ancilla in writing oracles. And here this might be a little bit hard to read, but we wrote a compile function, and it takes in a Boolean expression, and it returns a circuit. So it's easier to read the circuit than it is to read the code, probably, especially if the code is illegible because the contrast isn't good and it's small. So we have some number of inputs, x and y, just 2 here, but it can potentially be any number. We want to compute an AND of 2 expressions, b1 and b2. So we're going to compile b1 onto an ancilla 0. We're going to compile b2 onto another ancilla 0. We're then going to do a toffoli with those on our sort of main output qubit. And then we're going to reverse both of those operations so we can throw away the zeros, and we're going to get the AND of b1 and b2 on this wire q, and everything else should be in its original state. And then there's a lot of fun things we can prove about this. So the first thing we would always prove is that this is a well-typed circuit for any Boolean expression. And that's pretty easy. We have a tactic called type check that will do this for us. The next thing we want to prove is that, in fact, correct assertions compile B for any Boolean expression B. So that is to say that all of our assertions are valid. And this is just going to use our lemma that says, oh, the right kind of syntactic circuit is always using valid ancilla. But we could have a more complicated circuit that potentially can't use that lemma, and then we would have, then we would start reasoning about the circuit in more detail. So that sort of checks our boxes for ancilla. And finally, we might actually want to show that the compilation is correct. That is, if we have some assignment to all of the input qubits, then it produces the corresponding output to the Boolean expression. So we have our separate evaluator for the Boolean expression itself, and we can check the evaluator of the Boolean expression against the circuit and show that these two things are equivalent. So there's a few more applications of this. So one reason we care about these ancilla being correct is it allows us to do verified optimization. So if I have a circuit like that, maybe I don't want to bother discarding and initializing a new qubit, so I'll just make it go away. Another thing we might want to do is circuit reversal, and that's only valid if our circuit actually, I hope it doesn't spin too many times, okay, has valid ancilla on either ends. And finally, verified quantum arithmetic. That's sort of a, it's important to do, for instance, modular exponentiation for Shor's algorithm. We want to be able to verify that all of our arithmetic circuits are computing what you actually need to. And for that, it's important to have ancilla that you can trust. So that's it. And thank you.
Any questions? Yes.
So a really common optimization that you do in practice is any time ancilla ends up 0, you instead measure it earlier before the previous operation, and that tends to turn 2 qubit operations into 1 qubit operations. And so forth. Would the system be able to deal with that sort of optimization having been done?
So can you walk me through this slightly more slowly? So
suppose you have a C0 and another C0.
Sure.
Instead of doing the C0, you measure in the x-axis basis and then do a classically controlled Z on the original.
Okay. Yeah. So that's a nice optimization, and sure. I mean, it's not. So we have a hopefully ever-growing file of equations that sort of relate these things, and we have bits which are separate from qubits, specifically to denote a classical bit being used to control something. So some of our equations already let you jump between these two, between bits and qubits as necessary, because obviously if you measure a bit and then use it to control, you could also control and then measure a bit, or vice versa. So yeah, we should be able to add that to our list of equations, and then at some point we want to just have a rewriting system that uses all these equations and makes these circuits more efficient.
Any other question?
All right.
Sometimes when you do the measurement thing, the computation doesn't really look at all of the computation. So I don't know if you're paying really close attention at my talk yesterday, but the way we computed the AND was very different from how we computed the AND. And that's another thing that you could deal with.
Yeah, I want to get more detail on that. So the wonderful thing about the way we've expressed what it is for an assertion to be correct is that it is fully general. It captures all correct assertions. So that would be another. So certainly we want to have sort of better notions of better conditions for these things being correct, because nobody should have to delve into the actual denotational semantics to prove that their ancilla are being used correctly, because that would be a real hassle. So yeah, I think this is a really, that would be an exciting thing to implement.
All right, thanks Rob again.